Alright, so this is note 7 from CS70. This one is about public key cryptography. So the problem that we are facing is that we have these two people, Alice and Bob, and Alice wants to send a binary message to Bob over an insecure link. And the way Alice is going to do this is by taking her message, encrypting it with some function E, sending it over to Bob, and having Bob decrypt it with some function D. Now, it's possible that there is someone malicious, some possible attacker who's going to try to intercept that message and decrypt it themselves. So, in the beginning, it was just a private key system in which Alice and Bob would come together and decide on what function they would use beforehand to encrypt the message so that Bob could, take the inverse to decrypt. If you took 61B, you can think of Enigma, how they would the Nazis would relay what their codes were for, I believe it was for the month before going their separate ways and sending each other messages. But there's this other method that was developed recently called the RSA method. And in this network, each user has a public key and a private key. The public key is available to anyone, and the private key is only known by the individual user. However, if Alice sends a message encrypted using Bob's public key, only Bob can unlock it, because you can only unlock a person's public key with that person's private key, and the only person with that private key is the person themselves. So hopefully this makes it a bit more clear than what I said. Okay, now we're going to go over the mathematical scheme of it. So RSA relies on modular exponentiation and prime numbers. Those are just a couple things it uses. So we're going to start off with this value n. N is equal to p times q, where p and q are large 512-bit prime numbers. Okay, and then we have this value e. E is going to be a number that is relatively prime to p minus 1 times q minus 1. And if we remember what that means from the previous note, e and p minus 1 times q minus 1 have a greatest common divisor of 1, or in other words, e has an inverse mod p minus 1 q minus 1. Okay, so how do we put this in terms of the RSA protocol? Well, Bob's public key is going to consist of n and e. And notice how p and q are hidden. P and q are used to create n and e, but you can't just go backwards from n to get p and q, or go backwards from e to get p and q. And we'll sort of see why this is hard in a little bit. Okay, now what's Bob's private key? Well, if it's going to be the decryption, it's going to have to be the inverse of e, mod p minus 1 q minus 1. Okay, and again, we know that that exists because e is relatively prime to p minus 1 times q minus 1, or because the greatest common denominator is equal to 1. Okay, so now we're going to go on to what this looks like. So Alice is going to take some message x, some bits, and she's going to encrypt it by taking x, raising it to the power of e, which is part of Bob's public key, and then modding it by capital N, which is also part of Bob's public key. Okay, now Bob is going to decrypt e of x by raising it to the power of the inverse of e, and that will yield x. Okay, so yeah, maybe we can do a written example really quick. I'm going to switch over to Paint, so let me draw it up really quick. Okay, so just kind of following the order of things, P is equal to 5 and Q is equal to 11. The first thing that we are going to want to do is figure out Bob's public key, and if you remember what that looks like, it contains the value capital N and the value lowercase e. Capital N is equal to the product of P and Q, which is equal to 55. E is equal to the, let's see, it's E is equal to P minus 1 times Q minus 1, or I guess the inverse of, let me check actually. Sorry, so yeah, so E is relatively prime to P minus 1 times Q minus 1. So P minus 1 times Q minus 1 is going to be 4 times 10, which is equal to 40. And it should be relatively prime to 40. And that means the greatest common denominator between E and 40 should be 1. So E is going to be 3. E is going to be 3. And you can verify that the greatest common denominator, or sorry, greatest common divisor between the two is 1. Okay? And with that, we can take some message. Let's say the message is 13. And Alice is going to use Bob's public key to encrypt this message. Okay? And actually, really quick, so E is equal to 3, right? Something that we also have to have is D, which, if we remember, is the inverse of E mod P minus 1 times Q minus 1. And if we take 3, this value, and we take its inverse with respect to this, we'll find that it is equal to 27. And this makes sense because if you multiply 3 by 27, you'll get 81, and 81 mod 40 is equal to 1. So hopefully you see that. Okay, and now we're going to move on to Alice taking Bob's public key. She's going to take Bob's public key, and she's going to raise it to E, and she's going to mod it by N, where N is 55. And let me just check the notes for what the actual calculation for that is. Okay, so sorry, 1 second, so again, it's X is equal to our message to the power of E, and E is not 40. We established down here that E is equal to 3. So this is how Alice would encrypt a message, and in this case, this would be equal to 52 mod 55. Okay, and now if Bob wants to decrypt that message, he's going to have to take 52 and raise it to the power of the inverse of E with respect to P minus, inverse of E mod P minus 1 times Q minus 1. And you just sort of have to trust that this will actually yield 13 back again, which is what our original message was. Okay, and we're going to prove why this works in a little bit. So let me switch back over. Okay, so sorry. Okay, so we went over the example. Now we're going to go over, just really quick, Theorem 7.1 just kind of says that if we encrypt a message and then decrypt it, it should be equal to our message mod n for any message that is between 0 and n minus 1. So we're just kind of establishing that, but we'll actually prove it in a little bit. In order to prove that theorem, we're going to have to use Fermat's little theorem, and so we're going to talk about it here. So what it says is that for any prime number p, we're gonna, and any a value where a is a natural number up to but not including p, it's true that a raised to the power of that prime number minus 1 is equal to 1 mod p. Okay, so we're going to step through the proof right now. So let's come up with a set S, and let's define it as all of the possible numbers that a could be, right? Now, we could also take an arbitrary a and multiply that a by each number in the set, right? And there are, as we can tell, because there's no zero values, and we're multiplying by a different number each time, and all of those numbers, all of those multiples are smaller than our mod size, then we're going to get p minus 1 distinct numbers. And this means that S and S prime are the same set, just in different, not necessarily the same order. Right, so if we take S prime, we're going to see that it is mathematically equivalent to a to the p minus 1 times p minus 1 factorial, because we're taking, what is it? We're multiplying each term by p minus 1, p minus 2, all the way down to 2, and then 1. And then we're just, again, multiplying each term by a, p minus 1 times. And, yeah, okay, I guess I repeated this equation. Let me pull the actual other equation from the notes. Actually, I don't really have to. We can just show this. So, really quick, the first equation is what happens when we take the product of every number in S prime, and this second equation is what happens when we take the product of every number in S. Okay? But as we can see, because all of the numbers in S and S prime are the same, that means that, or sorry, to be clear, all the numbers in S and S prime mod p are the same. Because of that, we know that p minus 1 factorial is congruent to a to the p minus 1 times p minus 1 factorial in the mod p space. So hopefully that makes sense. And if that's the case, we can take the inverse of p minus 1 factorial, and we know that every number leading up to p has to be relatively prime to p, because p is a prime, so the only number that divides it is 1, and every number leading up to that, the only common divisor with that number, the prime number, has to be 1, right, because it's smaller than that prime number. And because every number is relatively prime, then the product of all those numbers is also relatively prime, and if two numbers are relatively prime, then one number has an inverse mod another number, right? So that's sort of explained out here, and because of that, we can take the inverse of p minus 1 factorial, and we get 1 is congruent to a to the p minus 1 mod p. Okay, next we're going to use Fermat's little theorem to prove 7.1, which basically just says that if we encrypt a message and then decrypt it in our mod space, then, you know, this should be something that we should do, basically. Okay, so again, we encrypt by raising to the power of e, we decrypt by raising that to the power of d, and we're going to say that that's equivalent to x mod n for every x from 0 up to n minus 1. Really quick, e times d is equal to 1 mod p minus 1 times q minus 1. Again, e and d are inverses of each other, mod p minus 1, q minus 1, and so it makes sense that they would have 1 as their value, because remember, x times y is equal to 1. Then we're just going to represent this in its sort of arithmetic form, where we're going to say that ed is equal to some multiple of the mod value plus the remainder, which is 1. Now there's a formula for that. And we're basically going to look at this equation right here, x to the ed minus x. We're going to sub in this expression for ed, and then we're going to factor out an x. And what we want to show is that the above equation is equal to 0. Okay? And we're going to do that by assuming arbitrarily that one of our prime numbers that makes up n is a number that divides x. So we're just going to say that p divides x, so it could be the case that p does not divide x. So if p does not divide x, then x mod p does not equal 0. There's some remainder there. So by Fermat's little theorem, x to the p minus 1 is congruent to 1 mod p, and you can sort of look back at what we previously stated to confirm this for yourself. And if this is the case, if x to the p minus 1 is equal to 1, then this x to the p minus 1, that becomes 1, so 1 to the k times q minus 1, that whole thing becomes 1, and so we have 1 minus 1, which is equal to 0 mod p. Okay, and also something I'm a bit confused, I'm not entirely sure why we can just say we can use Fermat's little theorem mod p on x, because x can be any number mod n. So because of that, it can be any number from 0 up to but not including n. However, p times q equals n. So couldn't it be possible that x is actually larger than p? That's why I'm a bit confused. But anyways, I'm going to gloss over that. So yeah, in the case that p does divide x, well, we have to show that this equation, this last side, equals 0. And so if p divides x, then this side would become 0, and this whole equation would become 0. Okay, and that sort of shows how this comes out to 0. So what does that tell us exactly? Yeah, basically we take this, which is the encrypted and decrypted function, we subtract it from the original message, and we're showing that by subtracting them we will have a value of 0 because they are equivalent. So hopefully that makes sense. And really quickly, why we use RSA. I'm kind of just going to skip through this, but why we use RSA, essentially it's hard to crack because there is no efficient algorithm for determining x, and the reason is because it's very hard, or it's considered very hard, to find two large prime factors of n. And it's compared to that, it's relatively feasible to implement because we just have to find Bob in this case has to find two prime numbers, and we can say that they have 512 bits. And if they have 512 bits, then we know from the prime number theorem, which was just given to us in the notes, that roughly 1 in every 355 of all 512-bit numbers is prime. So it's not too difficult to find two prime numbers to multiply together to get our capital N. And similarly, we have to compute exponentials mod n, and we sort of talked about the runtime in the previous note when we are doing x to the y mod some n, and the method we use to execute this is repeated squaring, and we know that takes about O of n time. And because we have because our number is represented in bits, it's the number of bits with respect to our number is actually O of log n, where n is the number. And so our actual runtime is more like O of log n, and then because we're multiplying bits together, it's takes O of m squared, and then the total exponentiation runtime is O to the log n cubed. I didn't really confirm this for myself, but I sort of just took it for granted from the notes. But other than that, that is pretty much everything there is to this note. This has been Note 7, Public Key Cryptography.